Hello there. Uh, I realize that the output on this channel has been steadily slowing down, but that's mainly because I've been engrossed in this e-book or whatever, the MIT thing, and trying to remember what I can from the past about these things. Well, this data structure called a descriptor and descriptor tables, selectors and whatnot, and finding out some things that, well, I don't know if I ever knew. Maybe I did, however many years ago when we did this manually, that I've been wrong, and I said, well, I've had a wrong idea, I think, about these the values that appear in these registers. Okay. So the first thing I can say is that I'm going to make a correction, but it's a kind of it's the kind of correction one would like to make. To do with the last video where I had claimed having proved that the model here is flat. No, tacitly, well, there's nothing wrong with the proof, right? It is true that from the experiments we did, although we didn't try every single possible offset, the model is flat. When it's not flat, you would expect things to be out of sync right away. It would have been highly unlikely for all those things to line up over and over again, to the same value. However, these numbers are not really the end of the story, and it all has to do with this segment translation, they call it. And I believe I've read this correctly. So what we have in our world, in terms of address lookups, are these segments and offsets, right? Here's an example of an offset, and these are segments. We know that one is misaligned. These other ones are definitely aligned, right? But one thing, I might be wrong about this, but one thing that appears to be the case, and this experiment should not prove it, but indicate to you, well, no, it proves one thing. This experiment, what I'm about to do, proves one thing, that this and this being the same, having the same numeric value, in no way implies that they refer to the same thing. And here's the demonstration of that. I'm going to put into dx, which is currently 1, CS23, 1B. Okay, 1B offset this. it should give me the value A, B, C, D, 1, 2, 3, 4. And there it is. Okay? Now I push CS on the stack and I'm popping it into GS. Okay? And it's even showing me that presumably at GSAX is the value ABCD1234. But watch what happens when I try to actually access that. I get an access violation. This thing goes back to 0, and a whole bunch of flags get set. It's still saying this, by the way. I don't know if that's an artifact left over. But anyway, we had two numbers. There was 1B. I went out to this line again. If you didn't see, 1B, 1B, and I have just used 1B, but just, I don't know why the highlight is showing a 32-bit value for CS, but maybe in this view it does, I don't know what how the debugger interprets those. That's something else, I don't know. Anyway, I have just done 1B colon EAX, and I haven't changed EAX from what it was originally. It's the address of I. Now, so therefore, this line and this line, in terms of numbers, right, are identical. And yet one works and one doesn't. I get a crash. Well, so that at least proves one thing. What it proves is that the comparisons that we did, like DS offset against ES offset, those returning the same value is not a given, right? So the actual test for flatness is stronger than previously. I thought that these tests didn't show anything because they're all the same number. But when this was the same number, I got a different value. So there's something else behind these numbers. Now they keep talking about selectors. Okay. Now, so selectors and descriptors are selectors are in a sense indices for something called a descriptor. Somewhere in memory, there is one major table called the global descriptor table. Okay, that just happens to be the case. There may be more. There might be a fake, right? This virtual machine might have its own fake global descriptor table, and then there are local descriptor tables, which are presumably a per process thing. Okay, and this is the format of an entry in a descriptor table. Now there are two, let's say, that there are two formats. Okay. Illustrates the two descriptor formats. Now, stare at that for a while and see if you can find the difference. And if you haven't found it by now, there are two things that are different. 1. This for the user code and data segments rather than the operating system. This bit is 1, operating system 0, and there's an extra bit called A for the user code, user descriptor. This is a descriptor, not a table, which is 8 bytes long. And there's a bit, a single bit, which is the first bit of the 6th byte, right, in the list. 6th? 1, 2, 3, 4, 5, 6, yeah. So the first bit of the 6th byte in a descriptor with an extra flag, so the type is smaller, I guess, right? Type is, this would have been, this is, I don't know how many bits go in these values. But it adds, if you read this the way you're supposed to, it goes from right to left, 0 to 31, that's 32 bits, and then 0, you're at byte 4, 0 to 31, byte 8, for 8 bytes total. Okay. Now that's what a descriptor looks like. Not very much difference between the two types. And a selector, okay, I'll show you this in a second. A selector extracts something out of a descriptor table. So it's like an index, but it's not exactly an index. Part of it's an index and part of it's something else. But first, let's just have a look and see if there's anything else I missed before going on. As far as the flags, those will come up as I'm reading through the other thing. This AVL, okay, it's shorthand for available. I'm not sure why that's there. Not what I thought. This had that, might be that property. There's something called privilege level, granularity, which is almost going back to DOS. Present, that sort of says that says that whatever this refers to. If this is a 1, then this refers to something, and if this is a 0, then it refers to nothing. It's not present. Okay, it's a descriptor that's not present. So, well, it's a descriptor that refers to nothing. All right. Now, a descriptor is to be found in one of these tables, and it says quite clearly that for the global descriptor table, the first entry is never used. It's just for some reason they always leave that blank. Where does it say that? Probably in this section. Probably in the descriptor tables. Okay, now it's a descriptor tables, an array of 8 byte entries, each entry being a descriptor, as I just described. A descriptor table can contain up to this many entries, and there's a reason why that is, you'll see in a minute. Now, read this slowly. The first entry of the GDT global descriptor table index equals 0 is not used by the processor. Okay? I've read that line about 30 times just to be sure, 100% sure that there's no mention of local descriptor table in this sentence. This is referring only to the global one. Because I got confused. Here it's got GTR. Here's the unused thing. And then the entries are filled up or not. But the way they've drawn this one looks the same. Even where these N's and M's are, I don't know what they mean, but it would appear as though this is also unused, but there's nothing in the text to indicate that, so this just might be that somebody got lazy and just copied this diagram to this and didn't bother to, erase this part and bring this down and add one more, right? Okay. Now, so now I've just showed you the layout, what all these things mean. Base defines the location of the segment. We're talking about segments and segment translation, and a segment is defined by a descriptor. The descriptor tells you everything you need to know about a segment. And presumably a selector retrieves you a descriptor from a table, and then you can work it out from there. So base. In both of these cases, base, I don't know why, it's all split up and mixed up, but there are 32 bits worth of base. 16 here, 8 here, and 8 here. So they've written it down at least so you can see it's going from 0 to 31. That's 32 bits. So the segment, therefore, can be based anywhere within a 4 gigabyte space. And it even says that. Now, limit. The limit of the segment, that tells you basically how big it is. Now that limit part has only 20 bits. See? Same for both. 16 here, and you don't even have to figure it out. The last one is 9-bit 19, so that makes 20 bits. Okay, and this is going to tell you how big the segment is. The segment referred to by this descriptor, not any table, specific element from one of those tables. But we've only got 20 bits. All right. So we put the 20 bits together, and then the processor interprets this field in two ways depending on the setting of the granularity bit. So the granularity has only two possible values, 0 or 1. If 0, the granularity, what they call a granularity, which would be like in DOS, the granularity is 10 hex bytes or something, right? It tells you that that the elements in the space, in the address space of the segment, the elements one element will be of a size defined by a granularity, and if the granularity byte is 0, then it's 1 byte per. It's broken up into units of one byte each, and that means that you can have up to 1 megabyte long length a segment 1 megabyte in length, because you've only got 20 bits. Or if that bit is 1, then we go to the maximum, right? Amount 4 gigabytes. The way to get to 4 gigabytes is to make the granularity 4K. So that means that the segment is broken up into chunks of 4 kilobytes. Now, I just happen to know that that this is the one that's used. Well, because you know too, because we're able to access up to 4 gig of memory. It said that this same document said that if the size is only 1 megabyte, we can't do that, and there are only 2 possibilities. So therefore, the granularity is 4K, and the whole memory arena is broken up into an array of 4K, what they call pages. Okay. Whenever they talk about memory, they talk about pages, and one page is 4K. Now, I was trying to get to I did the correction already. Almost. Yes, I did. The correction was that that test that what was it? Three. For 3 of the segments, those weren't null tests; those were meaningful tests, and so the result is clearer evidence of the fact that it's a flat model. Okay, now there's something called type. What does it say, type? Now, both of these, both variants of a descriptor have a type thing, and it doesn't tell you what they are, which is good. Too much information at once. Privilege level, again, cleverly they're leaving it. They're not going to discuss it. They're going to tell us about that later, because just in understanding the layout, it's not relevant, right? Okay, present bit I mentioned, whether the thing is there or not. If it's 0, the descriptor is not valid, right? And any use of a descriptor with a not, which is got this p equal to 0, it's not present, will cause an exception. And that exception will occur when a selector for the descriptor is loaded into a segment register. Now that's interesting. Okay. There's an exception though. There's an exception. You can put 0 in. It says it's somewhere. We'll get to it in a minute. So you can use things marked available. And now there's something called segment-based virtual memory, where the operating system, on purpose, clears the present bit, even if the thing is present. to cause an exception to occur, and then in that way they can implement things called something called paging, memory paging, virtual memory, or it just might not be present. Accessed, okay, all this basically tells the operating system is whether or not the segment is like in use, basically. Okay. The bit gets set when someone accesses the segment. Okay. And that occurs when a selector for the descriptor is loaded into a register, or there's a special instruction, selector test instruction, and virtual memory is sometimes implemented by a mechanism that periodically tests and clears the access bit. Okay, so you have the present and the access bit, two mechanisms to implement virtual memory. Okay, no problem. Now here's where things start to get a little bit unexplainable. Here's an example of an empty descriptor, right? Here are the instructions that you're not allowed to call. I mean, the user code can't use these instructions. Only operating system code can use them. This is load global descriptor table and save global descriptor table. And this is load local descriptor table and save. Okay. Privileged instructions, and you're not allowed to execute them. That would cause a processor fault. So you can never, as a user mode, in the user mode, you can't actually look at what the values of numbers are. Now this is the part where things get messed up. And I'll show you in a minute. Why? I'm pretty sure the documentation is correct, but I'm pretty sure that the interpretation. Well, let me just show you. Okay, here's a selector, a 16-bit value, right? Which I saw, and I've probably thought this for years, that these 16-bit values that look like segment values, I thought these were selectors. However, here's the layout of what a selector looks like. It's 16-bit, sure. There are 4 bits that are reserved for these flags, and then another 12 bits on the end. Now, there are 3 bits for this part, privilege level, and 1 bit for table indicator, and table indicator specifies the descriptor table within which to search for the descriptor that belongs with this selector. Now our values, brought this up to demonstrate. We have CS, we have, that's 1B. We have DS and ES and all the others, 23, and FS, 3B. Okay. Into binary, that part's easy. This part's easy. 1 and B here, that's 8, 9, A, B, 3, right? 8, 9, 10, 11, which is B. Now this here would be bit 15. This would be 8, 4, 2. Now to recall this picture, 3 has a meaning. So I'm going to separate these. Okay, so 0, 1, 2, 3, and well, let me write them all out first. Uh, 23. Oops. Right? That's a 3. And that's a 2. The last 4 bits are split up. 3 and B is the same as that one. Okay. Now, according to this document, what we have is index, and then the table indicator, and privilege, requested privilege level. So in the first case, the code segment, we have table index 1, so the first descriptor in the table, whichever table it may refer to, table 1 and privilege 3. Okay, and this one, DS, in fact, I'll put DS at the top, because that's the data one, the one that we look at more often. That has 2 for the index of its descriptor, 0 for its table indicator, and 3 for privilege. And FX has 3 for the entry in table 1 with privilege level 3. The lower the level, the higher the privilege. So 0 is the highest privilege. 3 is lowly level. Now the part that doesn't make any sense to me. If this were true, so that means that the data's descriptor for my program and every other program is entry 2 in the global descriptor table for the machine. So it's global, not per process. And the code segment is, so the code descriptor is entry 1 in the local descriptor table. So that this is, per process, right? You see where it's going wrong. Now it might be a typo or something in the document. That's another possibility. The FS thing, use the same format. That's entry 3 in the local. Okay? Oops. I'm so used to saving. Now, that doesn't make any sense. Every other program in the world is using DS23, right? And unless the global descriptor table is not global, and it's possible, of course, and it's some kind of fake global descriptor table. Unless that's true, then my data is in the same address space as every other program, right? And although the code loads always to the same address, static data, which still uses DS, right? Like the static read-only data or whatever, is using this segment. I don't use CS to access static data. So that's simply impossible because every program would be using the same. These would map to the same physical address. You see what I'm saying? First, why aren't they all local? Is the documentation incorrect? I could see code as being sort of a shared resource. It could be, its descriptor could be in a global table, but that can't be the case because every program loads at the same address, right? So they can't have the same descriptor in the same table. So why is this a 0? If this were a 1, I wouldn't have any problem. Everything should be local, right? But it's 0. It's very strange. Everything else sort of makes sense. Then I went to this part. Segment registers. Now wait a minute, I thought we were just talking about segment registers. Aren't those the 16-bit CSS things, right? Now wait, hang on, there's something here other than CSS. Oh, okay. It does not cause an exception when the segment register besides these two is loaded with a null selector. Okay, that's nothing. Okay, so that's not the story. So that's not what a segment register is? Well, no, it says. Every segment register has a visible portion and an invisible portion. Figure 5.7. The visible portion is available for use by programs. You saw I used it and made everything crash. And the invisible portion is used by the processor. Now, in order to modify these registers, you use special special instructions like this that I've been playing with, and I was successful in modifying GS. What was my experiment here before? Okay, here I just used push and pop, right? And I'm going to show you why I then went to try this. Because push and pops are not good enough, apparently. If we use these instructions, then the program loads the visible part of the segment register with a selector, and then the processor automatically fetches all of this data, base address, limit, type, and all the other descriptor table, descriptor information from the descriptor table referred to, and stores it in the rest of the register and that would be at least another 8 bytes. So that's a 10 byte register, and we can see 2. So that our view here is only a small portion of what's in here, right? 23. There's 23, and then there's all this stuff, which is if it's not a full descriptor, it's most of it, because it has the base address, which is 32 bits, the limit, which is another 20 bits, type, and more, right? And the reason it does that, the reason it stores that information there is for speed. It stores information from descriptors in segment registers, okay? It doesn't say near segment registers or anything like that, right? So therefore it doesn't have to keep looking it up from the table. So these registers, and this is probably no coincidence, have a short part and a long part. It's not, 32 bits. It's much bigger. It's probably 10 bytes, I'm guessing. Now this, according to this sentence, if I'm reading it correctly, if I use one of these instructions to try to set the value of when this push and pop didn't work, but if I use one of these, the processor should automatically fetch all of the data from the descriptor table and store it in the rest of the say GS register. But I tried it, and it's some sort of half work, but whenever I try to use it, it crashes, it doesn't work. Now, it says in plain English, our normal program operation, okay, you don't have to be the operating system in order to run these instructions. And so there's nothing here none of these are privileged instructions. I can show you one of them working. And it'll change GS. Through one of those instructions. Now I gotta set it up in a special way. Actually, I've got one example set up down here. I made a struct. I know this seems like a waste of time, but I was trying to figure out what this is the instruction I want to use. It's called load full pointer. And what these instructions do is they load the descriptor into the segment. In protected mode, in either of these cases, whatever I'm specifying is getting loaded into the segment register. Okay. Now, the operand for LGS can be 30. On the left-hand side, you can have a 32-bit thing, and on the right-hand side, a full pointer. Full pointer is 32 plus 16 bits, which is 48 bits. So this is a 48-bit full pointer. Okay, and here we have GS and either 16-bit or 32-bit extra thing. Okay. And I saw an example somewhere, and it works sort of like I've got it here. Now, the thing that kept happening to me was I would get a crash whenever I'd do the load. And then I realized, well, I'm not sure still how it works, but if I do it this, here's P. P here consists of a pointer and a selector value. You can try it either way, right? That's what I was trying to do. Such that the address, let's say DS and EAX is pointing at P. So DS EAX gives me a 48-bit value, which is supposed to be loaded into GS and the remaining part EDX. Now we'll see what happens. See if it works. Question is, how does it load it in? That is, do I have to reverse numbers and stuff? Maybe that's true. I don't know. But and I haven't actually. Yeah, no. I've given this thing a valid pointer value. If it wants a pointer, I'm assuming it could be that it needs a pointer, or maybe it should just be a number. And tried a whole bunch of things, and I can never read from this GS. And I'm not sure why. Okay, now here in EAX is the address of P. Okay, and that is, here I'm taking it that the last word value is it's broken up into, I'm thinking D word and word. And it succeeds. You'll note first that DX became this value, which is P. Okay, so EAX, no, it's not the same as EAX. P is on the stack. Okay, so into E, this is almost like a load effective address again, right? In fact, it probably is. That's what we're doing. We've loaded the effective address of P into GSDX. Now, does that make sense? 23, that is the effective address right, of this object P, which is on the stack. Now, how come this has changed? P, no, wait a minute, that's the value of P. No, it's the value of offset. Oh, it's the value of point I see. Okay. I here. I's got garbage in it, but its address is a valid number, and the address of I is the number that got put into DX in this instruction. And so it copied the first part of this struct into DX, which is address of I, and the selector part into GS. It should be, according to the docs, now it should have taken this selector and loaded from the appropriate table, a global descriptor table, with these rights and index 2 or whatever, all the properties of any of these ones. So different from push and pop. I don't care what goes in DX, but watch what happens. I get an access violation and everything clears out again. Even though it's showing, it indicated that EAX, GS EAX should give me address of I, which it does. So it's very confusing. I'm not really sure. Anyway, that might seem like a waste of time, but I thought I'd get it out. And maybe you can think about it and see if you can come up with an answer. And this is unrelated to what I want to do. I want to do something much simpler than this. But I thought I was getting somewhere. You know, when this succeeded, you know, and that together with the documentation, I thought for sure I'd successfully loaded a segment, right? I'd created a brand new segment, an extra segment that you could use. In fact, it would be great if there were another segment I could use, and maybe I could make one like FS that has a different starting address. But what I think, and because of another page I found, because I don't know if I still have it here. I couldn't find any example online of the use of the instruction, except for this here. No, there's nothing to say what data 1 is or anything. Oops. It's not explained or anything. Load ES and FS, right? ESI and FS from data 1. Now data 1 is presumed a far pointer, like a far pointer. And what I think should be there at that spot is not my structure thing here, but perhaps an actual descriptor. But I'm not sure. The other documentation says that part should occur seamlessly, that the processor should load that from the descriptor. See, it even said automatically fetches the base address, etc., from a descriptor table, not from the thing passed into this instruction. So I don't know. It's a mystery. Just so I can call this an aside, but I'll keep it together with the rest. I may have to cancel the upload that will be going on as I watch through it I just recorded, but I have to insert this bit at the end anyway. I believe I'm pretty certain I understand now why those things. Is it? Yeah. Why those FS and CS. Where I run to the crashing. Are their selectors select for a local descriptor table. I'm going to take it as given that each virtual machine has its own private global descriptor table, which is global to the process. Okay. and that's described by these entries. These ones use a different descriptor table called a local descriptor table. And the reason for that, I believe, is because these things are things that, the values of these things are per thread. That is, their thread. Each thread gets its own will get its own descriptor table in the process, and when a thread switch occurs, these values are loaded from the local descriptor table for that thread. Now you can see why that might be the case, because this doesn't just speak of address, right? There are I lost it. I took the document away. But in the descriptor, there's more than just the address lookup, right? That part's the same, but as well, table of contents. Remember, it was 5, I think, somewhere around here. Okay, there are various flags, like is being accessed, present, privilege level, and so on. Sometimes one thread might run at a different privilege level than another thread in the same process, and that's why it would retrieve it would have to have its own private descriptor, right? That given thread, let's say, runs at a higher priority or has a higher privilege level because it's been granted. When we talk about NT security, sometimes a thread can elevate its privilege level, something, right? So there are these various flags. And type, I don't know, I haven't read what all these types are, but all of these things can be different, and they're definitely things that would be per thread. I also know for a fact that FS is a per thread thing. When you dereference FS, you'll get different values depending on which thread you're in. That's not true of any of these registers. That is, but all of them are going to read. Well, not this one, but all of these are going to give the same address. But the flags and permissions and various attributes of these things don't change from one thread to the next. But these ones do. These are per thread things. So it is my belief, although I haven't read it explicitly, that the model is that every process gets its own private global descriptor table, and for every thread in the process, there is a local descriptor table which contains code descriptors, code segment descriptors, and FS descriptors, that describe that segment and its characteristics and properties. So I think that's the answer. Definitely, this can't be system-wide global, right? None of them can, because they all translate to the same addresses, right? And they can't be, and so therefore it can't be referring to any global, numbers. I mean, the number, the offset parts are the same for every process. So the globalness here is global for all threads, and the localness here is thread local. That's my contention. Okay, I'm going to click this on the end, and hopefully I won't have to interrupt the upload to cut out something, correct something else.